Equilibrium of a rigid body, ENS 231, statics of rigid bodies. Now, at the end of this session, you guys are expected to be able to develop the equations of equilibrium of a rigid body, introduce the concept of the free body diagram for a rigid body, and be able to show how to solve rigid body equilibrium problems using the equations of equilibrium. Okay, now as shown, this body is subjected to an external force, right? This one on the right side, this rigid body, it's color blue one. And it is not just subjected to an external force, but also with a couple moment system resulting from the effects of gravitational, electrical, magnetic, or contact forces caused by adjacent bodies. Now, the internal forces caused by the interactions between particles within the body are not shown in the figure because these forces occur in equal but opposite collinear pairs and hence will cancel out, a consequence of Newton's third law. So let us say what this means is that if you have your, let's say this is your rigid body, right? And a certain force is applied here. And if you are to cut that rigid body here, then that rigid body becomes this area here. So this is F. Whatever our value of F here will also be this value of F prime. Hence Newton's third law and the opposite collinear pairs and they will cancel out. Now, using the methods of the previous chapter that we had on equilibrium of a particle, and as not just that, but also the topics we had on force and couple moment system that acts on a body, it can be reduced to an equivalent resultant force and resultant couple moment at any point, arbitrary point O on or off the body. Now, if this resultant force and couple moment are both equal to zero, then the body is said to be in equilibrium. So mathematically, the equilibrium of a body is expressed as your resultant force F sub r, which is equal to the sum of all your forces, is equal to zero. And of course, our resultant moment about point O is equal to the sum of all the moments that acts about point O is equal to zero. So basically, equilibrium of of a rigid body is just the same with our equilibrium of a particle. Only the main difference is that for a rigid body, this time we will be considering forces that are non-concurrent, right? So they are still coplanar, but they are non-concurrent because in equilibrium of a particle, it must be that our forces are concurrent, meaning all of the line of action of all of our forces passes through a single point. Now, it is different, just like what we had in our previous topic, which is on force and couple moment systems. But again, since it is in equilibrium man, uh, if we sum all of our moments and if we sum all of our forces, it is equal to zero. Okay, so let us take this for example. Now, we will consider a case where the force system acting on a rigid body lies in or may be projected on a single plane. And furthermore, any couple moments acting on the body are directed perpendicular to this plane. So this type of force and couple system is often referred to as a two-dimensional or coplanar force system. Now, for this topic, we will focus first on equilibrium in two dimension. Now, for example, the airplane in the right has a plane of symmetry through its center axis, right? So that is represented here at G. And so the loads acting on the plane are symmetrical with respect to this plane. Thus, each of the two wing tires will support the same load, which is T, which is represented on the side view, which is 2T. It means that whatever weight our plane has, it is supported by the tire at the back and the tire at the front. So of course, if you can observe, since the weight, which is weight of our plane, which acts at the center of gravity, is directed towards closer to our, as refers here, the wing tires, which is our 2T. So a much greater reaction is exhibited here at 2T. But nevertheless, there are still an ample amount of force that our front tires is exerting. Okay, now for a copy of the centroids formulas of centroids and as well as the illustrations of how to visualize various reactions in any rigid body system will be uploaded in the Google Classroom. So please browse through that. Now, successful application of the equations of equilibrium requires a complete specification of all the known and unknown external forces that act on the body. Now, the best way to account for these forces is to draw a free body diagram. So we have talked already of what a free body diagram is, and you have started uh, drawing some free body diagrams. But in here, in our study in equilibrium of a rigid body, it is very desirable and it is very helpful that we represent our forces on a free body diagram. Now, this diagram is a sketch of the outlined shape of the body, right? Which represents it as being isolated or free from its surroundings, such as free body, hence the name free body. Now, in that sketch, it is necessary to show all the forces and couple moments that the surroundings exert on the body. So we already did this in our equilibrium of a particle, but this time we will just add another uh, factor into our free body, and that is moment. A thorough understanding of how to draw a free body diagram is of primary importance for solving problems in mechanics. So if you are still having a hard time constructing your free body diagram, please visit our slide on equilibrium of a particle. Now, before presenting a formal procedure as to how to draw a free body diagram, we will consider the various types of reactions that occur at supports and points of contact between bodies subjected to coplanar force systems. So, of course, we have many types of reactions, but majority is usually we will encounter what we call pin connected, which resist horizontal and vertical force, and as well as roller, which only resist vertical force. Now, as a general rule, a support prevents the translation of a body in a given direction by exerting a force on the body in the opposite direction. So let us say if we look at this figure here, if I have a force going down, my reaction, which is here at pin, it will also resist that. Because if I don't have that force going up to counteract this going down red arrow force, my rigid body will go down, right? It will move. So our support prevents translation. Also, if I have uh a force that is going down to the right. So my horizontal force F sub x resists that force. Now for pin, it supports a horizontal and vertical force, while a roller, sorry, uh, supports only a vertical force. Now, a support prevents the rotation of a body in a given direction by exerting a couple moment on the body in the opposite direction. So, usually, if we have this kind of structure here, fixed support structure, which is sometimes referred to as our cantilever beam, if I have a force going down here, so it creates a clockwise moment about this point. So therefore, this support my rigid structure here at the end will exert a force opposite to my arrow going down, so that is why I have F sub y going up, and a moment this moment here. Although this is just a representation, but the moment must be going down to counteract this initial moment that we have here. Okay, now when the body is subjected to a system of forces which all lie in the XY plane, then the forces can be resolved into their X and Y components, right? We already classified this one as following the principle of moment, which is the Verignos theorem. Consequently, the conditions for equilibrium in the two dimensions are, we have summation of forces x is equal to 0, summation of forces y is equal to 0, and summation of moment about O, for example, or any certain point is equal to 0. And the equation above is most often used for solving coplanar equilibrium problems. Now we have what we call alternative sets of three independent equilibrium equations. That is, we're also allowed to have, let us say, if you want to solve it via taking the moments lang without summing the forces x or y, you can also do that. You have summation at one point, another point, and another point. So that is summation moment about A, about B, and about C is equal to 0. A summation of forces, it can also be represented as a summation of forces x is equal to 0. Moment about a certain point, A is equal to 0, or B is equal to 0. What does it mean is that if for two-dimensional problems, in order for us to completely solve our problem, it must be that we either use summation, force summation, x or y, and then take the moment. Or if we want, we can also just do all moments, or do one summation and then two moments. Yeah, it must be we use uh, three sets of equation to solve for our equilibrium problems. And separate video will be uploaded for example 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which is, I believe, quite many already, in hopes that we can really thoroughly grasp the idea of solving equilibrium problems for rigid body systems. Now, sometimes there is what we call two or and three force members. What does it mean? Is that, as the name implies, a two force member has forces applied at only 2 points on the member. An example of two force member is shown in the figure, letter A. Where's my cursor? So later, we will learn that in order for us to completely solve our force using the equilibrium equations, summation of forces x, y, a moment about a certain point is equal to 0, it must be that more than there must be more than three or more forces, right? But for this case, but that doesn't mean if we only have two forces, dili na nato masolve. No, there is a technique for that, and that is why these two and three force members exist. Now, an example of is shown. Now, to satisfy force equilibrium, we have force A, F sub A, and force F sub B must be equal in magnitude. So it must be F sub B is equal to F, and F is equal to F sub A to make it that F sub B is equal to F sub A, so that they act in opposite direction. And if you sum their forces, it will be equal to zero. Now, furthermore, moment equilibrium requires that F sub A and F sub B share the same line of action, which can only happen if they are directed along the line joining points A and B. Again, this is to satisfy a summation moment that our moment summation rather, that if we do moment summation, it will be if we do yeah moment summation, it will be equal to zero. So it must be, they must follow the same line of action. So that if we do moment about B, so you will not be considering F sub B because the line of action of F sub B passes through point B. Now, if the force that is being applied at A also passes the line of action of F sub A, which is applied at point A, also passes through point B, then their moment summation is equal to zero. So therefore, for any two force member to be in equilibrium, the two forces acting on the member must have the same magnitude and it acts in opposite direction and have the same line of action, directed along the line joining the two points where these forces act. And knowing that, we will have this kind of example. 12, 13 is also a pin connected, three force, uh, no, a two force member. Example 14, the same, 15 as well, and 16. So like I said, a separate example with videos for the 16 examples will be provided.